let's look at this problem where we have random Poisson arrivals. By random, I mean the Poisson arrivals usually have a parameter lambda or mu. Here I'm going to assume that that parameter is also random. So this usual randomness due to Poisson, and then where the so I could call, we will call it doubly Poisson arrivals. So of course, by Poisson arrival we mean events arrive randomly, like packets or etc. So whatever we denote here, this is the waiting time to the first arrival. This is the second time waiting arrival. And let's say we make some observations. We observe all the first n waiting times. So just to recall Poisson arrivals from my other videos, if it has a parameter lambda, then these waiting times are independent and they have exponential distribution. That's the story with but here the parameter itself is random. So the point here is what can we if we have all this data, which is we have observed the waiting times of first n arrivals, what can you say about the next one? When will it arrive? How long it is going to be? Can we get some idea about tau n plus 1, the next arrival? So that's sort of the problem. We want to infer that from this data in this messy situation. The lambda is random here. That's the whole point. So as I said, if the density function, all this tau is for a particular lambda, in other words, if lambda happen to be constant, then it is well known, it's an exponential distribution, lambda 2i. You can refer to my videos. So, and whereas here we'll assume the lambda has, f lambda has some distribution. Let's say I will start with also some other exponential. And this is where I'm going to start. So question is, what about tau n plus 1? How much can we push this to get some idea about tau n plus 1? So tau 1, tau 2, etc., tau n are the waiting times to the n arrivals. This we just measured it. So this is the data. This is sort of with us. And tau n plus 1 is unknown. So we want to predict something about or infer about tau n plus 1 from the above data. So first, to make this, so the question is, how do you update our knowledge about lambda in presence of all these observations? So we have the a priori PDF of lambda to be exponential. So this is the a priori PDF. So that's like this. Then we have the data. So all we could say that the if you look at tau 1, tau 2, etc., tau n to proceed this given lambda. So for given lambda, all these are independent random variables from standard theory. And each of these are exponential with the parameter lambda e raised to minus lambda tau I. So this turns out to be lambda I e to the power minus sigma tau I multiplied by lambda I equal to 1 through n. And I'm going to call this as lambda n e raised to minus lambda tau, where I'm just going to define tau to be tau summation of tau I. So this is from the data known. So this is the conditional density function of tau 1 through tau n given lambda. So to find out the unconditional density function, we'll use the Bayes technique. So we want probability of tau 1, tau 2, etc., tau n. So that's going to be average it out on as we did on few other lectures on lambda. So if I do that correctly, so this is going to be lambda n e raised to minus lambda tau, then mu e raised to minus mu lambda d lambda 0 through infinity. So this is 0 through infinity, mu goes outside, lambda n e raised to minus lambda mu plus tau, mu here, tau here, multiplied by lambda, d lambda. So to make progress, I'm going to call this a new variable, mu plus tau multiplied by lambda to be y. So that lambda is y over mu plus tau, and d lambda is dy over mu plus tau. So that this integral, the density function of tau 1, etc., tau n, becomes from here mu integral 0 to infinity. So instead of lambda, I'm going to substitute this. Instead of d lambda, I'm going to substitute. So this becomes yn e raised to minus y dy. And there is also denominator, which is mu plus lambda, mu plus tau, and to the power n, and 1 power here, so n plus 1. And so the answer is mu over mu plus tau to the power n plus 1, integral 0 to infinity yn e raised to minus y dy. So this you can do by parts. It's a standard gamma integral, it's n factorial. So the way you do this is do it by parts. The derivative of the first part is n yn minus 1 e raised to minus y minus n yn minus 1 derivative of e raised to minus y. That's minus e raised to y. So when you substitute top bottom limit, this goes to 0. This becomes the same integral with the 1 power reduced. So the whole answer is n factorial. So if you, the total answer would turn out to be mu plus tau to the power n plus 1 for tau 1 positive, tau 2 positive, etc. So that's the density function of that's the unconditional density function of y1, y2, etc. yn. So this is for each tau I positive. So now we can use these two, this result, to compute the a posteriori PDF of lambda. So we want lambda given tau 1, etc., tau n. So that's going to be joint density function of tau 1 through tau n given lambda multiplied by f lambda divided by the probability density function of tau 1, tau 2, etc., tau n. So I have all that, so let me just substitute them here. And so the first quantity is lambda n e raised to minus lambda tau, and this is mu e raised to minus mu lambda. And divided by tau n factorial, the joint density function we just found out, n factorial mu, the whole thing divided by mu plus tau to the power n plus 1. So this goes in the numerator, mu cancels. So we have mu plus tau to the power n plus 1 and lambda to the power n e raised to minus lambda plus mu lambda e raised to power mu plus tau to the power multiplied by lambda. Mu plus tau, the common parameter is lambda. So this is for lambda positive divided by n factorial. So That's where we are. So we have the a posteriori. So we have updated the observations. This is sigma tau I equal to 1 through 1. So the observations have come in here and here. This looks like more like gamma function. But in any case, we have the a posteriori PDF. And if you want, we can use this to get an update on the best estimator for lambda using the map estimator and so on. So to do that, we'll take the, let's say we take the logarithm of f. So we have a, all this has nothing to do with lambda, and we are going to take the derivative with respect to lambda. So let me call the log of this to be just constant, some constant with respect to lambda. Then you have n log lambda, and so this whole thing has come into here, and then minus mu plus tau multiplied by lambda. So we take the derivative of this with respect to lambda, and that gives us, notice that n over lambda minus this constant mu plus tau equated to 0. So this gives you, and this is when lambda equal to lambda hat map. That gives lambda hat map to be n over mu plus tau. So this is where the observations come in and gives you a prediction for lambda. Lambda is unknown, and in fact it is random. Previously it has we assumed it to have a prior of exponential. But but we are more ambitious. Our problem is how can we use this knowledge to get some idea about tau n plus 1. Tau n plus 1 is unknown. We haven't measured it. So we want to do prediction or infer about it. So the first thing is, the question is, well, can we figure out its density function for tau n plus 1? So notice the density function of tau. So of course we want to make use of the data also. So density function, to start with, the density function of tau n plus 1 given lambda is easy, because it's once if lambda didn't happen to be, this would be just an exponential. So we will condition it on lambda. Would be to find out the unconditional density function of tau n plus 1. Except we don't want to simply go to waste of what we have learned so far, which is the a posteriori PDF, which updates our the measurements into the it gives you the updated information or about the lambda, the unknown parameter. So the whole point is that of in inference, we will, to bring in learning, we will remove the we will replace the a priori by the conditional density, posterior density function of lambda given the observation. So that's the a big step. So I'm going to obviously substitute that. And this one, for a given lambda, this is going to be, of course, lambda e raised to minus lambda tau n plus 1. So let me replace this tau n plus 1 by a easier variables, lowercase t, so that's easy to compute. So now I'm going to substitute for everything, since I have. So this is going to be integral 0 to infinity. Remember the variable, so I'm looking for f tau n plus 1, and I'm going to change this variable to lowercase t. So this is going to be lambda e raised to minus lambda t, and then I substitute for the a posteriori PDF in place of f lambda. So that's going to be a mu plus tau to the power n plus 1 over n factorial, then lambda n e to the power minus e to the power minus lambda plus mu, I mean mu plus tau multiplied by lambda. So this is the posterior density function need to be well. So I'm going to do it obviously in the next page. And let me collect all the lambda terms together and the constants outside other than everything lambda. So I have f tau n plus 1 equal to mu plus tau to the power n plus 1 over n factorial integral 0 to infinity lambda to the power n plus 1 e raised to minus mu plus tau from here t. So just keep adding this multiplied by lambda d lambda. So I'm going to call this whole thing to be z. So I'm going to define z to be mu plus tau plus t multiplied by lambda. So that lambda is z divided by mu plus tau plus t, and d lambda is dz divided by mu plus tau plus t. Let me not make any mistakes. So this gives us, let me substitute it. So f tau n plus 1 z, t rather, is mu plus tau to the power n plus 1 over n factorial. If you notice, we can do this mentally. This is e raised to minus z, and d lambda is dc over this factor. Lambda is this over this. So this comes out to be integral 0 to infinity z to the power n plus 1 e raised to minus z dz, except this denominator factor is so you have n plus 1 from here, one factor, so this is n plus 2. So this turns out to be mu plus tau to the n plus 1 over mu plus tau plus t to the power n plus 2, because this is all so mu plus yes, mu plus tau to the power n plus 1 over mu plus tau plus t to the power n plus 2, and then there is an n factorial in the denominator, integral 0 to infinity z n plus 1 e raised to minus z dc. So this is as before n plus 1 factorial, and that cancels with n factorial, just giving n plus 1. So which, let me simplify, let me rewrite that. So that gives f tau n plus 1 t to be n plus 1 from here. Then you have mu plus tau to the power n plus 1 divided by mu plus tau plus t to the power n plus 2 for t positive. So that's where we are. And so recall that this tau is where the observations come in. Tau is I equal sigma tau I equal to 1 through n. So now the question is, what next? We have the unconditional density function of this this random variable, which we are yet to measure. Well, we may not be. We are somewhere here, so we want to make a prediction about idea. So obviously, with the density function in hand, at this point we can look at its average value. So that's going to be integral 0 to t multiplied by f tau plus 1 t dt. You just need to do this integral. So if I substitute it, so the t variable, you can check this very easily. This is a PDF. You just integrate it. Area will be 1. So this will turn out to be n plus 1 mu plus tau to the power n plus 1 integral 0 to infinity t over all the terms involving t. Now what? So to make, see, t is here and here, so we can get rid of the numerator t by adding and subtracting this. So I'm going to add here mu plus tau, and then I'm going to subtract this here. So notice that this will take out one term, and this is just a constant. So this will turn out to be n plus 1 multiplied by mu plus tau to the power n plus 1 integral 0 to infinity 1 over mu plus tau plus t to the power n plus 1 here, one term less, minus mu plus tau integral 0 to infinity 1 over mu plus tau plus t to the power n plus 2. There's no change here, dt. So we have to deal with these two integrals. So let me make the obvious substitution, mu plus tau plus t equal to u. So expected value of tau n plus 1 . So then we have multiplied by, we have two integrals. Notice that when t is 0, the lower limit is mu plus tau. So this is mu plus tau here instead of 0. Upper limit is infinity. And this is dt is du. So this is u to the power n plus 1. Minus, we have one more term, mu plus tau integral, same lower limit, mu plus tau to infinity, 1 over u to the power n plus 2 du. So we can integrate both these terms separately, each of these terms. So this is n plus 1 mu plus tau. So this is 1 over, so u to the power minus n plus 1 plus 1. So that's minus n. So minus n u to the power n mu plus tau infinity mu plus tau here minus n plus 1 u to the power n plus 1 in the denominator, same limits, mu plus tau infinity. So if you substitute this, if you simplify this, so notice this will be, the top limit is 0, so minus minus will become plus, so this will become 1 over n mu plus tau to the power n. Here mu plus tau, top limit is 0 again, minus minus goes away, so this will become n plus 1 to the power mu plus tau to the power n plus 1. So notice one power of mu plus tau goes away. Then mu plus tau to the power n is common, pulls out, it will cancel with this. So you'll get the result to be 1 over n minus 1 over n plus 1. So this is 1 over n multiplied by n plus 1. N plus 1 cancels. So this will turn out to be mu plus tau over n, I guess. So that's going to be, remember, tau is sigma tau I plus, so you can rewrite it this way. So the expected value is the average value of all the previous n observations, which is what we would have assumed the common sense wise. But you have a correction factor or the penalty due to the randomness, mu over n, where mu is a, remember, the exponential parameter. So this is what the Bayes inference tells us about prediction, the average value, expected value of that tau n plus 1 is on the average a little tiny bit more than the average. Of course, this correction factor will depend on what which prior we have used. We have used exponential prior. Suppose you use something else like gamma or something, then of course it's going to be more complicated. And this is the way to, so the whole point is, this is the way to include prior knowledge together with the data to update and make predictions about what's going to happen. So this is a good example. Thank you.